Hi there. This section is entitled Ratio and Root Test, two more specific tests for series. Now, ratio tests, we're looking for series that are kind of mixed up ideas. Well, one thing is factorials. Anything with a factorial pretty much is going to be a ratio test. But something like this one, 2 to the n over n cubed, where one term is geometric, one term is polynomial. So you're kind of looking for mixed things like that to be your candidates for ratio tests. Now let's take a look at how the ratio test is applied here. Let's see. And we take, so assuming our series is non-zero terms, now the series AN will converge absolutely, although I don't really use the absolutely terminology that much like we do with alternating series. Converges, I believe, is sufficient enough for this, but it's absolutely strictly because they have an absolute value. That means if you're performing this on a series that has alternating terms, you can essentially just ignore the negative because the absolute value will take care of it. But this says that we evaluate a n sub 1 series over a sub n. Now, a n sub 1, you'll see when we start looking at some examples here, a n sub 1 is literally just taking everywhere you see an n and place it within n plus 1. And then we evaluate this ratio, and if it's less than 1, it converges. So you would say your series converges by the ratio test. If it's greater than 1 or also including infinity, we have diverge. And then the ratio test is inconclusive if it equals 1. So that means it won't lead you to the wrong answer, but that means you should have tried something else, or should then try something else. Now, unlike the limit comparison test, where it was a fraction, it didn't matter the numerator or the denominator, which series you put on top, which one you put on the bottom, the one you're testing, the one you're comparing, it doesn't matter. But this absolutely has to be a n sub 1, n plus 1 over a sub n. In fact, here's an important statement here, and we'll see some more of these at the end of this section. Ratio test will lead to inclusive outcome for all problems where we should have used LCT for polynomial. So when it's just polynomial terms like this, that actually, when I say polynomial, you can actually have a square root or something or things like that. There's no point in applying the ratio test because you end up, here's a n sub plus 1, put n plus 1 in there. I'm not going to go through all the details on this because it's not really applicable to what we're going to be doing. Anyway, long story short, you work this out, you get an n to the fifth over n to the fifth plus all smaller terms. That ends up equaling 1, which right here, that's inconclusive. So meaning it didn't tell you anything. So yes, you should have done an LCT with 1 over n because you have an n squared over n cubed, so that's what makes it 1 over n. And that would have been the proper way to test this. But now let's look at some actual ratio tests. Let's take a look. So we have 2 to the n over n factorial. Well, that n factorial gives it away as being the ratio test. So I'm going to replace these with n plus 1. So it's 2 to the n plus 1 over n plus 1 factorial, and then divided by the original series, which then, dividing, flips over the original series to this reciprocal. And in fact, what you're going to see me start doing after this is a little shortcut, is you don't have to write the series as original fraction. It's always going to be the n plus 1 times the reciprocal of the original. So you can go right to this step over here every time without having to write that first step, just to save you a little extra effort there. So now we have to simplify. Now back in the sections on sequences, we learned how to simplify factorials and haven't had to do that in a while. But let's take a look at this. So n plus 1 factorial can be written as n plus 1 times n factorial. So you can review that section on sequences if you needed to see this again. So you stop it at n factorial, which then allows you to cancel those n factorials. So you have an n plus 1 left on bottom. So I guess technically I could have canceled this out too, I guess, couldn't I? Because obviously this was replaced with n plus 1 times n factorial. So, okay. Didn't have to do that, but didn't hurt. And then on the top, since 2 to the n plus 1 is the same thing as 2 to the n times 2 to the 1, you cancel 2 to the n's, and that would leave you a 2 on top. And then we kind of clean that mess up, and we come down here, and we're trying to evaluate what's the limit as n goes to infinity of 2 divided by n plus 1. Well, of course, that's going to go to 0. 0 is less than 1, converges by the ratio test. And you're not responsible for this part over here. But we're just trying to establish whether or not it converges and by what reason. The only types of series that we actually want to find the sums are geometric and telescoping. But I just put this in maple just to show you, and it does converge. That's a real number, e squared, so converges by the ratio test. All right, let's take a look at this next example. We have n cubed over 4 to the n. So you replace n with n plus 1, so you have n plus 1 cubed. Over, you replace n with n plus 1 on the bottom. You have 4 to the n plus 1. And then times the reciprocal of the original function. So I'm already going into that shortcut that I mentioned in the last problem. Instead of writing the one big fraction, go ahead and just write the reciprocal of the original right here and save you some effort. Now, similar to the last one, I didn't write it out here, but 4 to the n plus 1 is 4 to the n times 4 to the 1. So the 4 to the n's cancel out and leave you a 4 on bottom. Now, let me come over here and show you what's going on. Now, obviously, these terms do not cancel algebraically. In other words, from an algebra standpoint, they don't cancel. But keep in mind, we're evaluating these as limit as n goes to infinity. So if you come over here and look at this, the limit of n plus 1 cubed over n cubed will be 1, because the numerator is going to be n cubed plus some smaller terms, which are insignificant when you're approaching infinity. So essentially, it's just n cubed over n cubed. And then, and you don't need to do 3 L'Hopital's rules to resolve that, but it would work. You can do it 3 times and it would work, but actually you can just say n cubed over n cubed is 1. So that is why I can cancel that there, strictly because of this limit. So that does go to 1. So I want to clarify that, because that might look weird that, it looks like I didn't know anything about algebra or whatever, but no, it's because of this reason right here. So I'll probably won't go through each time, this comes up again, and it will. I probably, won't go through the detailed explanation, just to realize it's going to be 1 every time. So I have a 1 on top and a 4 on bottom, and that gives me 1/4. There's no n's or anything there. Well, of course, 1/4 is less than 1. So we have converges by the ratio test. Once again, I just put that in maple for grins, and there's what it actually converges to, which in no way are you responsible for finding that. And as I mentioned in that statement right here, so I was just showing you those sums just for the heck of it. Now let's take a look at this one. It's basically the last problem flipped over. So I'll kind of skip past the details here since we've already kind of done this one. See, it's the exact reciprocal of that one. I'll leave it right here, that way we can see both of them. And then, so this time the 4 would be on top, and the same reason as before, these two cancel to be 1, so you're left with 4, and then that's diverges by the ratio test. So I'm assuming I'd put this one in maple, it would show probably infinity or something like that. So you see, so you flip it over, then all of a sudden it diverges. Now let's take a look at the next one. We have n times 10/9 to the n. So I kind of broke that up here. I broke the 10 and the 9 up separately. So then I replaced, don't want to erase that. And so you see all the n's are replaced with n plus 1s and times the reciprocal of the original series. And same kind of logic right here, that these don't cancel algebraically, but they cancel limit-wise to 1. And this time you have a 9n plus 1 to the bottom and a 9n on top, so it leaves a 9 on bottom. Top, you have a 10n to the n plus 1, and then 10 to the n on bottom, so it leaves 10 on top. So that's all going to simplify to 10 over 9. That's greater than 1. Diverges by the ratio test. There we go. So once you get the hang of this one, now this one's a little interesting, and I'll be honest that, unlikely that I would specifically put this on an exam, but I thought it was worth taking a look at. N to the n over n factorial. So you see I replaced both those n's with n plus 1, so it's n plus 1 to the n plus 1 over n plus 1 factorial. The reciprocal of the original, n factorial over n to the n. So using the simplification rule for factorials, n plus 1 factorial would be n plus 1 times n factorial, which cancels the n factorial. Now, I purposely did this to get rid of the n plus 1s, which will actually cancel algebraically this time without the limit necessary. But I broke this, that was necessary to break this n plus 1 to the n plus 1. So n plus 1 to the n plus 1 is the same as n plus 1 to the n times n plus 1 to the 1. You'd add those exponents to get n plus 1. That cancels, and that leaves us n plus 1 to the n over n to the n, which now, because they're the same exponent, I can put them all together in parentheses, and I have this expression right here, which if you broke that up into two fractions, it would be 1 plus 1 over n to the n, and that is famously the definition of E, actually. In fact, and I'm just mentioning here, if you refer to my notes on the L'Hopital's rule, we work this out, except we use x instead of n, but it does work out to be E. So if you want to go back and see how that was done, that's where you have to define the limit as y equals and take the natural log of both sides and go through those steps. Because this is one of those indeterminate forms, it would be 1 to the infinity. So, probably unlikely I'd put this on a test. But long story short, it does work out to have an answer at E, and then E is greater than 1, so we have diverges by the ratio test. So I found that one to be kind of interesting, and look at this. Put that all right in there just to show you that it did produce E. But we actually have the skill set to work that out ourselves. All right, there's what I was just saying, okay? Highly unlikely or extremely highly unlikely. Now this, I try to avoid problems on exams that have the negatives. I don't want people to get this confused with alternating series tests. But as I go over here, I put the absolute value. You can see I ditched the -1, got rid of it, because the absolute value is going to make everything positive anyway. So the -1 just goes right away, so it's almost pointless to have it there, frankly. So I don't think that was that big of a deal. So I just ignored the -1 to the n because it's just going to be all positives anyway. 1 to the n is just 1. Now, very common mistake here. Sometimes people like this 2 to the 4n, they would put 2 to the 4n plus 1, thinking that's the next term. But no, you replace n plus 1 with n like I did right there, and then so both the n plus 1 is multiplied by 4. So technically you have 2 to the 4n plus 4. So a very common mistake. Same thing down here. A lot of people would put 2n plus 2. But actually, no, it's 2 times n plus 1, because n plus 1 goes in for that n. So 2 times n plus 1 would be 2n plus 2. Then we add this 1 right here, and it makes it 2n plus 3 factorial. So we start with the larger factorial, which is 2n plus 3, and we work our way down to where we match the top part. So 2n plus 3 factorial is going to be 2n plus 3 times 2n plus 2, and the 2n plus 1 factorials cancel. Then on the top, the 2 to the 4 n's would cancel, so you're left with 2 to the 4th. So we have 2 to the 4th, which is 16, or over a couple of n's multiplied down together on the bottom. Okay, so you got a number over n as n goes to infinity. That is clearly 0 from a limit standpoint. So 0 being less than 1, we have converges by ratio test. And there we go. Now let's take a look at the root test. This is an interesting one here. It's pretty easy to work with. And you're going to see it's primarily for series where their whole thing is raised to the nth power. So essentially, or it could actually be some multiple like 2n or something like that. But anyway, this just says you take the nth root of what you have and then look at the limit of what's left, take the nth root, and if that's less than 1, it converges. So it kind of has the same converging and diverging rules as ratio test, but the way you evaluate them is differently, though. You know, with the ratio test, we have the an plus 1 over an. So you're basically just taking the nth root, and it's diverging if it's greater than 1 or infinity, and it's inconclusive if it equals 1. And so I'm mentioning right here that this, okay, just telling you that anything that's geometric would also be root. Reduce the size on that for a sec. Okay. But not by, this is just saying if it's geometric, it's also root, but all roots are not geometric. Like certainly this next one is not going to be geometric. So it's really easy to use. So this is 2n, and you can tell that this is a root test because that outside exponent to the n, that is the key. That n right there on the outside, that power. So literally all you're doing is taking the nth root of that series, which means taking the nth root of the nth power means you're just removing the n. So because n times 1 over n is just 1. So you're just taking away the n, and then you evaluate that limit. And that limit, you can do L'Hopital's rule if you want to, but you can clearly eyeball it, see it's going to be 2. So that limit equals 2, greater than 1, diverges by the root test. Here's another one. So once again, it's all raised to the nth power, so it's going to be a root test. Remember, geometric, so this is, you might be wondering why aren't these geometric? It's only geometric if there's a number on the inside of the parentheses. You can't have n's in there with it. They're only numbers to be geometric. So you take the nth root of this series, which means you just remove that exponent, take the limit of what's left, n minus 2 over 5n plus 1, that's going to be 1/5. So since 1/5 is less than 1, we have converges by the root test. This is really pretty easy. Take the nth root of this one, takes rid of the exponent, now you have ln over n. So we've got an extra step to do here, but not difficult, because technically ln over n is infinity over infinity. So we have to do L'Hopital's rule for this one. I realize like for this last one, you don't have to do L'Hopital's rule when we're talking about just powers of n or whatever. That's no big deal. But since we have an ln there, we need to kind of do L'Hopital's rule, since you're not just matching exponents. So the derivative of ln of n would be 1 over n. The derivative of n would be 1. ln of 1 over n, then goes to infinity. Limit of 1 over n would be 0. 0 less than 1, so it converges by the root test. Now this one's e to the negative 3n. So you take the 1 over n, that still leaves you an e to the negative 3, which just kills the n but leaves a negative 3 there. That's fine. And which is 1 over e cubed, and you can easily verify that that's less than 1. You don't have to know that. You can verify that in the calculator. That's a root test. Now this, of the root test we just did, this one is the only one that would actually be geometric. Because this e to the negative 3 right here on the inside, if you rewrite it like I did right there, where you put the n on the outside, e to the negative 3 is a number. So therefore, that's what would make this one geometric while the other ones are not. All right, very good. So this is just like the other sections in this book. I like the way they do this. They just kind of, at the end of each section, they just put some problems in there that could come from this section or any section prior to these. And this is the last section that we'll actually be doing these series tests on. Now there's still some stuff coming up later on called power series and representations of functions as series. That's a little bit different. But this is the last of these specific tests here. So we basically, up to this point, all the tests that apply to series, I'll just sort of say them verbally. Nth term test for divergence. And we have geometric. We have telescoping, p-series, integral, direct comparison test, limit comparison test, alternating series, and now ratio and root test. So that will conclude the list of all those. And let's look at some of these. Now, when you have multiplied constants, they can be pulled outside. So that is a p-series. If you had like n plus something or n minus something on the bottom, it wouldn't be a p-series. You would have to compare it to a p-series via limit comparison test. Diverges, p-series, integral. One of the things you're going to see down here. In fact, I think I will scroll down here for a second and show you this, and then scroll back up. Here's some things I added just to sort of show you how they kind of relate to each other. Any geometric can also be tested with root, ratio, or integral. Diverging geometric is also root, ratio, and integral, but if it's diverging geometric, you may also include the nth term test for divergence. Root series can also be tested by ratio, but not vice versa. And we mentioned this earlier, ratio and limit comparison test are incompatible. And then any p-series is also integral, but not vice versa. Not all integrals are p-series. So let's come back up here. So that means the fact that this first one here, the 100 over n, the fact that it's a p-series, divergent means integral test would also apply. The next one diverges by all kinds of, and I'm showing you, here's the formula for the integral, the reason why you can, that's why the geometric ones can be integrated. Because you can integrate a number raised to a power by using this rule right here. 1 over ln of a to the x plus c. That's why that can be integrated. Well, this diverges 5 different ways. So this also, because it's diverging geometric, that also means it's diverging nth term. But the key thing here is that you've got 2 times pi divided by 3, which is not between -1 and 1. You have to be between -1 and 1, not including -1 and 1 for the geometric to converge. This does not. It diverges. And in root test, you remove the n, it will diverge. Because 2 pi over 3 is greater than 1. It diverges by all 5 of those methods. Let's look at the next one. This one, limit comparison test with 1 over n, because you look at the n, or you don't have to worry about the 2, n over n squared. This could also be integrated. Yeah, a lot of times the integral test seems to apply a lot. It's hard to say, exactly when it's going to apply, but anything that can be integrated. This one's a pretty easy u substitution. You let u be the denominator and then du on top. It don't always assume integral is going to work, but it works a lot. Now, obviously, when you got stuff like the factorials and all that weird ratio test stuff, it's not going to work. This is a p-series because you can pull the 10 and the 3 out, and you've got 1 over n to the 3/2, but this one's a converging p-series. Unlike the one we did earlier was a diverging p-series. If p-series, then also integral would work. Some of these I have to admit, a little hard to see. Like this would be easy to do by the ratio test, which I worked out 2 to the n. It's kind of a mixed bag of stuff. But the nth term test would not be that easy to see here. I did illustrate it here, but I could see where that could confuse students, knowing that that one would apply. But the ratio test is pretty easy. You'll end up with a 2 on top. These limits will go to 1. The ratio will go to 1 from a limit standpoint. You have 2 on top, so 2 is greater than 1. But the reason why the nth term test works is I just happen to notice that the denominator is going to differentiate away. But anytime you take the derivative of a number to the n, all you do, every derivative, you just add, you'll be multiplying a natural log of whatever that base is. So, but the 2 to the n will never go away. So you see I have this, and it's infinity over infinity. So the first derivative, L'Hopital's rule, will give me 8 over 8n on the bottom. And all you do on top, it's 2n natural log of 2. And here it just puts another natural log of 2, so it's 2n natural log of 2 squared over 8. And now you've got an n over 8, so it's infinity. So it diverges. But that's a little tricky. Maybe I'd spare you that, on an exam of having to recognize that with n term test. But it makes an excellent ratio test question, though, because it's not that bad. Now, this is clearly an alternating series test because of the -1 to the n. And, well, you might think, well, wouldn't ratio test maybe apply? No, it does not. And like I said, I'm going to avoid the -1 for the ratio test. But this one, so the alternating series test says you can look at just 1 over that. That's clearly going to go 0. You get 1 over infinity. Now, I just put a check mark here because this is usually just pretty much rubber stamp, automatic. I haven't run across one yet where this wasn't true, but that means these terms are going to be decreasing. So if it makes it through the first one, you pretty much can assume it'll make it through the next one. So it converges. Now, that's all we needed for that one, but suppose you wanted to go one step further and know whether it was absolute or conditional convergence. That means you have to evaluate what that series is going to do. And test it without the -1, because then if it converges without the -1, you'll have absolute convergence. But if it diverges without the -1, that means it's conditional convergence because it had to have the -1 to converge. Now, I looked at this and I knew that limit comparison test is not going to work because of that ln. I thought about direct comparison test, but here's the problem with direct comparison test, because that one's so specific on the direction that it goes. So let's say I compare it with 1 over n here. Oh, I don't have a stylus to write with here, so I'm kind of having to freehand it. So if you're trying to get the problem with this ln of n, that means the denominator is larger than the denominator of just n itself. Okay, larger denominator means smaller fraction. So the inequality symbol would go this way. And unfortunately, that only works as if the larger series converges, because the direct comparison test says larger converges means smaller converges, or smaller diverges means larger diverge, because 1 over n is a diverging p-series. So this doesn't help us unless that inequality symbol would have gone the other way, because then you could have said smaller diverges means larger diverges. But you can't say larger diverges, smaller diverges. That does not work. So direct comparison test sometimes is convenient, but it's not useful here. So the best test for this one, unfortunately, maybe was the integral test. I couldn't think of another way to do this. But the integral is not too bad. So you see I wrote it as limit b goes to infinity. Of course, I changed it over to x. But it looks like it would be integration by parts, but it's not. It's just u substitution. If u equals ln of x, du would be 1 over x dx. So, but it does look like it would be parts, but it's not. So you end up with antiderivative then of just du over u, which is natural log of u. So you get natural log of x. And then I'll kind of just sort of cut to the chase here. As soon as you put the b in there, because the only thing that's really important here is what's happening with the limit when it goes to infinity. Like here, for the second, for the 2, you're just plugging the 2 in there, so you get ln of 2. That's, of course, that's a real number there. But it's what's happening here, whether or not this is going to converge or not. And ln of b will go to infinity as b goes to infinity. Granted, it moves very, very, very slowly, but it will go to infinity, so therefore you have diverge, and therefore that leads conditional convergence, meaning it only converged with the -1. Otherwise, it diverged. Here's another one that's the best way to test this would be integral. Yeah, so once again, if you tried direct comparison, that would not work. Limit comparison would not work, because if you compare it with 1 over n squared, the inequality symbol goes the wrong way. You need 1 over n squared to be the larger series, but it's not. The ln of n will be larger. Now, actually, the first couple of terms will be smaller, because ln of 1 is 0. See, ln of 3 is the first integer where ln is greater than 1. But then it keeps growing and growing and growing, so it's going to be bigger than 1 forever. So even though the first 2 terms aren't larger, they're going to be larger forever. But so you can't say smaller converges does not mean larger converges. I don't think I'm going to have you do a test problem where you had to do integration by parts, although, for your final exam, integration by parts is relevant. But let's go through this real quick. I'm not too concerned about this. But you remember, you have to let the u be the ln, and the du will be the other part. Or, I'm sorry, dv, excuse me. U is ln of x, dv would be x to the -2 dx. So that would antiderivative gives you -x to the -1. Derivative here gives you 1 over x. So you have uv right here, and then you have b du right here. So it's uv minus the integral of v du. So here's v right there. Here's du, which I just rewrote it as x to the -1, just to make it similar looking. So the 2 negatives here make positive, and then those 2 combine to be x to the -2. So when you integrate that, you get -x to the -1 again. So this would be the result if you were just doing an indefinite interval, which that would be easy enough. But now we have to bring all the limit business back into play here. Oh, looks like I didn't finish the problem. Okay, please. Okay, sorry about that. I didn't finish it, but I'll tell you that you would then have to evaluate the limit as b goes to infinity. I got that it converges to 1. There's what Maple's saying the actual series goes to. The integral converges to 1, but the series converges to a different number. And I've talked about that before with the integral test. Yeah, we're not saying the integral test is telling you what the series converges to, the actual value. It's just telling you whether or not it will converge. But I'll just say real quick that this is just 1 over x, so when you do the limit as b goes to infinity and you put in the infinity part, you'll get 0. But then obviously you've got a 1 part to plug in there. But this one, what you would do is you would drop the x down to the bottom, so you have ln of x over x, and then you would have to do one L'Hopital's rule, ln of x over x, and you would do that, then you would evaluate it, and that will produce a number. So evidently it ends up equaling, I believe that goes to 0. Anyway, you end up with 1 when it's all said and done, that it converges to 1 after you evaluate this part with the limit as b goes to infinity. Yeah, if I was using a tablet PC, I could actually write that out, but if I tried to freehand it would look too messy. But that's the key, is you would use L'Hopital's rule right here on this first part. Drop the x down to the bottom. And here's the list we were just talking about, how they relate to each other. All right, so that concludes ratio and root test.